Next, let's talk about transformation. So what's the motivation for transformation, or what's the goal of transformation? For example, let x1, x2 be a random vector. Suppose we know the joint distribution of x1, x2. We seek the distribution of the transformation of x1, x2. So that means you know everything about x1, x2. You know if they are continuous, you know the joint PDF. If it's discrete, you know their joint PMF. Now, what do you want to know? So there are many types of transformation. For example, you want to know G, X1, X2, Y. So what's the distribution for Y? That's one type of transformation. Or you can do another type of transformation here. You have Y1 is U1. So U1, X1, X2. Y2 is U2, X1, X2. So from X1, X2, you get a new random vector, Y1, Y2. Now I'm asking you, what is the joint distribution for Y1, Y2? So this is the transformation. For discrete case, actually it's straightforward. That's very easy. For example, let Px1, x2 be the joint PMF, discrete case. Now the transformation, we assume this transformation is 1 to 1. So 1 to 1 means you can get the inverse transformation. So the random vector, new random vector, y1 is u1, x1, x2, and y2, u2, x1, x2. What's the joint PMF? The joint PMF, we can work it out directly. For example, probability y1 equal to little y1, y2 equal to little y2. So that's the joint PMF. Now what is y1? It is u1, x1, x2 equal to y1, u2, x1, x2 equal to y2. Since the transformation is 1 to 1, so you can get the inverse transformation. The inverse transformation is here. So that means probability x1 is w1, y1, y2. This is inverse transformation. x2 is w2, y1, y2. So since I know the joint PMF of x1, x2, I can plug in to get the joint PMF for y1, y2. So for discrete case, if the transformation is 1 to 1, we can get the joint PMF of this transformation easily. Continuous case. So for continuous case, it's more involved. First, let's talk about a technique called the CDF technique. So let's consider this example. The joint distribution of x and y be uniform. So that's uniform. So the support is here, 0, 1, 1. So that's inside this triangle. So this is the support for x and y. It's uniform, it's a constant, 1. The problem is asking you, what is the PDF of this z is x plus y. So what is the distribution of z? Now for the CDF technique, let's work out the CDF of y directly. CDF of y, by definition, that's a probability x plus y less than equal to little z. So to evaluate this probability, it is a double integration. I'm going to using the what's random. X and y are random. X and y are uniform. Now this is asking you what's the probability x plus y less than or equal to z. So this is equal to the integration, double integration over this region. So, but this PDF, be careful, this PDF is 1 only over this support. So there are different situations. X plus y less than equal to z. For example, if z less than 0, x plus y less than equal to z is here. So there is no overlap with the support. The integration is 0. This in this region, among this region, fx is 0. z between 0 and 1. That's a x plus y equal to z. So x plus y less equal to z is this region. So the overlap is here. This is overlap. So now you can do integration 0 to z, 0 z minus x. So you get z squared over 2. There is a third situation is here. So it's z between 1 and 2. So that's the region. So its overlap region is here. So what we did here is 1 minus your integration over this side. So you can get a CDF. Now the fourth situation is z greater equal to 2, you will be here. So that will include everything. Include everything, essentially you will integrate your PDF over the whole region. It is 1. Now I can get the CDF of z. After you get the CDF of z, you take derivative. You can get the PDF of z. So this is the distribution of z. What is z? Z is x plus y. Now for the general case, let x1 and x2 have a joint PDF. Suppose I have y1 is u1 x1 x2, y2 is u2 x1 x2. So this transformation is 1 to 1. I can get the inverse transformation. I can define the Jacobian. So it's a partial derivative of x with respect to y. So it's x1, y1, x1, y2, x2, y1, x2, y2. So this is the Jacobian. Now my goal, what is the joint distribution of y1, y2? That's the goal. We can apply some multivariate calculus knowledge. So for example, let A be the subset of S. Let B denote the mapping of A under this one-to-one transformation. Because the transformation is 1 to 1, this event, so x1, x2 in A, is the same as y1, y2 in B. Because this is the transformation. This is A. You have a 1 to 1 transformation. So you will transform it to B. Because this is 1 to 1. So probability y1, y2 inside this B is same as probability x1, x2 inside A. Since I know the joint distribution of x1 and x2, this probability, I know how to do it. It's a double integration of A. You do integration of your joint distribution of x1, x2. Now what's next? The next, I need to do change variable. So I need to change x to y. So I'm going to let x1 be w1, y1, y2, x2 be w2, y1, y2. I change variable. I change variable. So if you change variable, you need to multiply the Jacobian. So now what do we get? I get a probability y1, y2 equal to b. Inside this b is a double integration over this b of some function. So by the definition, this function must be the joint PDF. So the joint PDF of y1, y2 is given by this formula. So this is how we get the joint PDF of transformation for the general case. We can take a look at an example to get a better understanding of this. So to solve this kind of problem, usually we will go through 5 steps. Now let's take a look at this example. Let x1 and x2 have the joint PDF. So this is the joint PDF. So you need to be careful about the support. x1 greater than 0, less than x2, less than 1. So let's draw a picture. What is support? So this is x1, this is x2, 0, 1, 1. So x1 equal to x2 is here. So x1 is less than x2. So x1 less than x2. That's the region. That's a support. So I have a bivariate random vector, which is defined over this triangle. Now I define the transformation. y1 is x1 less than x2. y2 is x2. So now I define a transformation. So the problem is, can you tell me what's the marginal PDF for y1 or y2? The marginal distribution. So let's go through 5 steps. The first step, let's get the inverse transformation. So you have y. Now let's get solve for x. So x1 is y1, y2, x2 is y2. Second step, let's calculate Jacobian. So the partial derivative of x over y. So this is a partial derivative. You get the determinant of this Jacobian, is y2. Now the third step is important. You need to solve for support. You need to solve for support of y1, y2. Don't forget this step. So x1, x2 is inside this support. You have a transformation. Now what is the support for y1, y2? The easiest way, you just plug in the inverse transformation back into the support of x1 and x2. For example, you get 0, y1, y2, 0 less than y1, y2. This is from 0 less than x1. x1 less than x2, this is from y1, y2 less than y2, and y2 less than 1. So for these inequalities, you will get y1 between 0 and 1, y2 between 0 and 1. So the support for y1, y2 is this, y1, y2. That's the support for y1, y2. So next, what is the joined PDF? Just write down the joined PDF. The joined PDF, you plug in the inverse transformation over here. You plug in the inverse transformation here and multiply the determinant of Jacobian. So you will get the joint distribution of y1, y2. Once you have the joint, you integrate out one of them, you will get the marginal. You will get the marginal PDF of y1, y2. So when you have this kind of problem, just try to follow these 5 steps to get the distribution of the transformation.